Hello, welcome to the Exam 2 review for OCHEM 2. This is for people who are taking Dr. Novak. So these are the main topics that I'll be going over. Um, I believe it should be ketones, aldehydes, carboxylic acid derivatives, enolates, some reduction reaction, alpha substitutions, and the Robinson annulation. So to start us off, um, I want to point this out first. If you guys have any questions, feel free to unmute or text in the chat. You can also raise your hand if you would like. Other than that, I'm going to continue on. So ketones and aldehydes, basically they're going to be C-double-O bonds, or C with an O with a double bond. They can be aldehydes or ketones. So it could be with a hydrogen or a methyl group or a alkyl group. They do have a resonance structure, kind of like this. These are all the other kinds of carbonyls. The more simpler ones are just ketones and aldehydes. The rest are what we call carboxylic acid derivatives. So an important feature of carbonyls is that the central carbon is sp2. They are shorter, stronger, and a lot more polar. And remember that polarity, higher polarity increases your boiling point. And with carbonyls, because it's a oxygen bonded to a carbon, there's no hydrogen bonding with itself. So with synthesis or making ketones and aldehydes, one way you could do it, so if you want to interchange with each other, you could do Grignard and an oxidizer. So over here, if you have an aldehyde, just react it with a Grignard. It should replace that H with an R group, the R group of the Grignard, and just use a strong oxidizer, just like chromate, and you'll oxidize this alcohol into a ketone. Okay. And then another way, so if you have an alcohol, you're starting off with an alcohol. If it's a primary alcohol, you can turn it to an aldehyde using a weak oxidizer. It can be like PCC, and DNP. If it's like abbreviated like these, or it's named after someone, it's usually going to be a weak oxidizer. If you if it's a secondary or if it's a secondary alcohol, you can just oxidize it, kind of like this, and it'll make you a ketone. And if you are starting with alkenes, you can turn it into a ketone or aldehyde using ozonolysis, where you'll cleave this double bond, and in return you'll have oxygens on both sides. So let's say if you want to add ketones in your benzene rings, you need to use Friedel-Crafts. Which is you use a acid chloride, and you react it with AlCl3, and it should attach to the benzene ring. It's going to favor if you have activating group or a electron donating group, it's going to land on the opposite of it, opposite or right next to it. So this is called the para position. This is the ortho position. And then so if you have an alkyne, um, if you react it with mercury and an acid, it's gonna do a what we call a Markov hydration. So here the double bond or the carbonyl will go to the one uh, next closest to a R group. If it's a terminal alkene, for example, in this case, it's a terminal alkene. It will try to make the double bond as much substituents as it can. And if you want to do the anti-Markovanov, where it here in this case it's an aldehyde, you would have to do hydroboration, which is the Ca2BH, and it'll just turn this into a aldehyde. So it'll turn this carbon next to the hydrogen. It'll give it the carbonyl, whereas the other one, it's the one closer to the R group. Another way you can make ketones when you have a carboxylic acid is organolithium. So it doesn't have to be like a phenyl group. It can be like any R group that you want to attach to the um, alcohol part of the carboxylic acid. So if you have two of these, it'll just replace that alcohol group on the carboxylic acid and turn it into a ketone. Next, if you have an acetyl, which is just um, two ethers next to each other on the same carbon, you can just do hydrolysis, which is just adding water. With this, it'll just combine, or it will, one of the ethers will leave, and this water will actually, yes, this is recorded, or this is recording. We will post this in um, our YouTube channel. Yeah, so by adding water, we can turn it to a ketone. Next, if you have nitriles, just you do adding Grignard can turn it into a ketone with the help of an acid. Also, the slides will be posted as well. Same with the review problems or the review problems and the key that we'll be going over the second half of the review. Right, so yeah, no problem. Okay, so if you want to turn a nitrile or any carboxylic acid derivative into an aldehyde, we just use dibol, which will turn it into an aldehyde. However, if the only exception is acid chlorides, for acid chlorides, you would have to use LTBA. That's shorthand for this long name over here. But if you use LTBA on acid chloride, it'll yield the same result as dibol, which is an aldehyde. So if you have an acid chloride and you want to turn it into a ketone, you would use lithium cuprates. Essentially, the R group of the lithium cuprate will just replace the Cl. This is kind of similar to the organolithium reaction. Let me see. Right here, where it will just replace a substituent of a carbonyl. Okay. Alright, so now we know how to make ketones and aldehydes. What can they react with to make certain products? So whenever you have a ketone or aldehyde, think of them as kind of like a substrate. So it's kind of like back in OChem 1 where you learned like SN1, SN2. This is kind of similar, where we have a nucleophile that will attack this carbon. So one important reaction that you need to know is called the Wittig reaction. Basically, if you have a pH3, this is called a yield. It will it will replace the group connected to the ppH3 and replace the oxygen with it. So this substituent right here, or this R group here, will replace this oxygen. Okay. So the mechanism for it is preparing the yield, where this is just a simple SN2 reaction. So where we have this leaving group, and over here this is going to be a um, like an elimination reaction, where you form that double bond over here. So what happens is when we finally make that yield, we can do SN2 attack on the ketone or aldehyde, and so just intermediate step where they like form a ring, which makes these two a leaving group, a good leaving group for um, when we do some kind. It's kind of like an elimination reaction, where we make that double bond over here. So overall, if we're starting not with the yield but with the actual R group that we want to attach, it's R group and the BR, which forming the yield will turn into ppH3, and it will just replace this oxygen with this R group while maintaining that double bond. All right, with that out of the way, we can talk about how do you make diols. Diols are just a carbon with two alcohols on the same carbon. So you can do acidic or basic catalyzed. They all form the same product. It's just different mechanism. Um, Basically, it will turn this carbonyl into two alcohols through so they will both do nucleophilic attacks on the double bonded carbon. Right. So if you want to make cyanohydrins, which is um, a carbon with a CN attached to it and an alcohol, um, you'll just do a regular SN2 attack and um, a proper workup to get that alcohol. If you want to make imines, which is instead of an oxygen, we have a nitrogen with a R group attached to it. We just use a primary amine, the R group being the R group that you want to attach it with. So by reacting it with acid, we will simply just replace the O with the N and the R, and we lose those hydrogens on the amine. So here are examples of the amine reaction. So other ways you can, other types of amines you can add as long as it's primary. So you can, here are just different R groups and the results you get. It should be the same mechanism. You just, whatever you have in a Z will be in the product. So if you want to make acetals, instead of diols, it's two ethers instead. So you just add two alcohols, two because you want two ethers on the carbon. And so, however, if you have one alcohol, it's just going to, instead of it becoming an acetyl, it'll become a hemiacetal, which is, instead of an alcohol, instead of two ethers, you'll get one alcohol and one ether. Right. So if we have a cyclic acetal, kind of like this, or if you want to make this, um, you would have to use a diol, so a molecule with two alcohols on it. So typically we do this to protect certain carbonyls. For, in this case, we want to protect this aldehyde. If we have an aldehyde and a ketone in one molecule, it will react with the aldehydes more readily. So here we could protect that aldehyde, and we can remove this acetal with hydrolysis. Okay. Yeah, here's a mechanism for it. So essentially, it's still that nucleophilic attack on the carbon. Yeah, so it's two nucleophilic attacks. If you want to make a aldehyde into our carboxylic acid, we just oxidize it with either chromate or what we call a tolerance test, where we react it with silver nitrate. It'll yield the same result, where we get an, instead of this H hydrogen, we'll get an OH. Right. So next part is reduction. So there's different kinds of reduction that we can do. Um, we can do BH4 stab or dibol. There's LAH, a strong reducer, halogenation, Clemenson or Wolff-Kishner, and here are the steps when you're reducing. Um, carboxylic acid derivatives being the um, most oxidized, and alkanes being the most reduced. Okay. So NABH4, they are weak reducers, so you can only reduce simple carbonyls like ketones and aldehydes, nothing else, and it will turn into an alcohol. Oops. So going back here, it will since it's a weak reducer, it'll just go one step to the next level of its reduced form, which is alcohol. Same. So with stab, what's different about stab is it will reduce aldehydes, but not if an aldehyde and ketone are in the same molecule, it will reduce the aldehyde instead of the ketone. So this is what it looks like. Another way of naming this is stab. So, however, if I were to if I want to reduce both carbonyls, then I could use NaBH4. Uh, and then with LAH, this is a strong reducer. It will reduce any carbonyl into an alcohol. So catalytic hydrogenation is just about it reduces simple carbonyls like ketones and aldehydes. What's special about this is that it will reduce double bonds or triple bonds. So here we have the double bond and then it's gone. A common reagent is rainy nickel, which is just nickel with H2. Another reduction is Clemenson, where we use zinc mercury with HCl. It will completely remove the carbonyl, so it will reduce ketones and aldehydes. Another similar way what you can do is do Wolff-Kishner, which is NH2NH2. It does the same process. It gives the same product as Clemenson, where we remove this carbonyl group and we just get a regular alkane. Okay. So we'll move on to the different kinds of derivatives for carboxylic acids. So basic structure, we have the carbonyl with a special group, which is over here. So if we have any of these would be their respective names. So here, the most reactive is acid chlorides, and then as you go down down to amides, you get less reactive. This is determined by the stability of the leaving group. So leaving group as in the X that it's attaching to. So we're ranking it on the stability of this X when it leaves. So Cl being because Cl is a electronegative atom, it's stable when it has that negative charge. And then as you go down, it gets less and less stable. Like for example, NH2, it doesn't prefer that negative charge as much as oxygen, for example. All right, so making carboxylic acids. So it's also shorthand for COOH. So here, if you would just want to make a carboxylic acid, we just figure out what our R group is. Here, it's an ethyl, and then just attach an MgBr and react it with CO2, and it'll give us a carboxylic acid. However, if you do this, it will also, if you have a molecule that has a ketone in it, it will also react with that. So this grignard will react with any C double bonded oxygen. Another ways you can do this, it's kind of like OCHEM 1 review, where you could do KMNO4, where you cleave alkenes. You can also cleave alkynes with basic. So with alkenes, it has to be acidic. With alkynes, it has to be basic. You can also do an ozonolysis with alkynes, and they will both give you carboxylic acids. With aldehydes, so if you have an aldehyde, this is the same slide as before, where we just oxidize it, or we could do a Toll's test. Um, you can also do H2O2. I didn't put that on the other side, but this is another way you could do it. It does the same thing. All right, so if you have a ketone, methyl ketone means that there's only a methyl attached to it. What you do is you do exhaustive halogenation, which is you fill up this carbon, this methyl, with halogens, whatever halogen that you want. It could be Br2 or Cl2, but basically you bombard this um, carbon with halogens. This makes it a good leaving group where the OH can do an SN2 attack and replace it with an OH. So if you have a benzene ring, you can replace any alkyl groups with a carboxylic acid using KMNO4 or a strong chromate like this one. Um, However, it doesn't oxidize T-butyl groups. So if you have like something that looks like a T, it's not going to oxidize. It's going to stay as is. Um, so here's the overview of all the carboxylic acid reactions. Notice that we can just react all the carboxylic acids with water and acid water to make a carboxylic acid. Um, if you want to go back up to acid chloride, you would have to use SOCl2 or C2O2Cl2. I call people commonly use SOCl2 or SOCL, what I like to call it. Um, it's easier to remember. So here you can't go from carboxylic acid to well, what you can do if you don't, as if you know the process of this, what you can do is you can just, if you want to go from ester to a anhydride, for example, right? You can just react it with water to get this carboxylic acid, and then react with salsa, and then you get acid chloride, and to get from acid chloride to um, thioester, for example, you'd have to use um, a thiol right here. All right. So the next topic is called the alpha substitution of carbonyls. So alpha is the alpha hydrogen. So the reason why it's called alpha substitution is we're talking about the alpha hydrogen. So if we have a carbonyl, the alpha hydrogen is the hydrogen um, on the adjacent carbonyl. So we have this carbonyl right here. So one carbon away would be this one or this. So it's when we deprotonate it, giving us a negative charge. So here we could do either or, depending on um, whether whether we add heat or not. So you can increase the acidity by adding resonance. So resonance makes this negative charge more stable. So we can add more carbonyls next to it and it'll resonate more. Um, You can also increase it by removing electron withdrawing groups. So an ester like this. Ester is a electron withdrawing group. So this is actually this actually won't help the um, negative charge here. Simply because these two oxygens, um, they are resonating with each other in the ester. So, I mean, it can still resonate it, but it's this negative charge will mostly do it with this ketone more. But usually these two esters are the one resonating with each other. So it's a lot harder for this negative charge to resonate with um, this ester. Oops. Okay. Uh, so how do you get that negative charge? To get a negative charge, what you can do is, react it with a base. The base will take that hydrogen away, and then you get that anion. And then for a lot of these reactions in the later slides, it's when this ion does a nucleophilic attack, whether it be SN1, SN2, and um, basically forms a bond with the electrophile. Right. So which hydrogen do we take? Do we take the hydrogen here, or do we take the hydrogen here? So if you have this is what we call, looks like, kinetic versus thermodynamic. So if it's cold, this is called kinetic. You would choose the one that gives a stable anion. So in this case, it will be the primary anion. The other one would be a secondary, which is less stable than a primary. So with a kinetic, you would take the one that's um, primary. If you're comparing with a secondary, so look for the stable anion. However, for thermodynamic, you look for the stability of the alkene. So after you deprotonate it, resonate it, so kind of like this, and see how that alkene is stable. So here we would have 3 substituents, right, on the alkene. On the kinetic version, we only have 2. So this alkene is more stable. So that if it's room temperature, or if there's heat, you would deprotonate the um, the alpha carbon that will make a stable alkene. Another good thing to know is what we call keto-enol tautomerization, where the double bond just changes places with a adjacent carbon, and this oxygen will turn into an alcohol. So these are both in equilibrium, but it'll favor the the ketone version more. All right, so let's look at the reactions of the enolate. So if you want to add more carbons to a ketone, we just form the enolate. You can do that by LDA. LDA is a strong base, which will get this hydrogen, and you get a nucleophile now. And you can just pick um, whatever, how many carbons you want to add, um, or any kind of alkyl group you want to add. Just stick it with like a good leaving group, and it'll just do a SN2 attack. So it's a special reaction called aldol condensation. So you still deprotonate it. So you still get that enolate ion. However, if you react it with another carbonyl, this is a nucleophile now. So it will attack this electrophilic carbon. So it'll do that SN2 attack, and then it will form that bond between the the ion and the electrophilic carbon. You'll end up with an alcohol, which you can remove by dehydration, which is the second step, by adding heat or acid or a base. So typically you just heat it up actually, and it will do an elimination reaction. So the acid base will make this into a good leaving group, and it will form a double bond because of elimination. Yeah, okay. So next one. So cross-aldol condensation. It The difference between this one and the last one is one has a alpha hydrogen, one does not, but it's still the same mechanism. It still does that SN2 attack and the elimination right after. Cyclization, same mechanism, but you're reacting in the same molecule. The same molecule reacts with itself. So it happens when you have two carbonyls on the same molecule. You'll know when you'll have to do cyclization when you're only given one reactant, and they give you a base to make that ion. So they'll do the S2 attack. Make sure you count your carbons between what's attacking and what's being attacked, so you can properly number your ring, and the whatever's being attacked and the attacker, they'll just make a double bond like this. And through dehydration, this carbonyl on the electrophilic carbon will leave, which is the elimination part. All right, so overall, these are a quick review. Um, if you have that alpha carbon here, or alpha hydrogen, um, what you do is essentially um, the oxygen on the electrophilic carbon gets replaced by um, the alpha the alpha hydrogen over here. So you still maintain that double bond when you think about it. You maintain this double bond. You just stick this, or you remove this oxygen and just put it on the side where the um, alpha hydrogen was. Okay. Um, so another reaction is Claisen esters condensation. It's still a mechanism, but instead of ketones or aldehydes, we have esters. So here with glycine, it's the similar mechanism, I'd say, but you skip the step where you form a double bond, so there's no elimination happening. So you can do cyclic condensation where it reacts with itself. Similar mechanism, but you don't make that double bond. Here, when you do ester condensation, though, um, your leaving group is actually um, the ether, one of the ether groups. So yeah, so it's the ether of the electrophilic um, carbon. So this enolate will, what is it? Oh yeah, this enolate will react to this carbon, and it will kick off this ether group. So yeah, same thing where this is the leaving group. So that's why you maintain this carbonyl over here, because this one doesn't leave. Um, so cross Claisen condensation, similar mechanism to the cross aldol condensation, but with esters. And um, one of the esters does not have a alpha hydrogen. Right. So what happens when you're reacting ketones and esters? So which one? What happens? What do you do? So with this one, ketones are prefer being the nucleophile. So here, find the ketone, which is, what is it? These are both esters. So if you have a ketone and an ester, the one that becomes enolate will be the ketone. That's because esters, this ester group is a electron withdrawing group, and remember from a few slides ago, electron withdrawing groups decreases acidity. So with having this ketone with no electron withdrawing group will that's how ketones are able to become the enolate ion. Right? Just a few slides left. But another reaction is decarboxylation. So basically, you remove carbon dioxide. So you only do that when um, you have this carbonyl, and it's what's called the beta carbonyl acid. So the beta carbon, so two carbons away from the carbonyl. So this would be alpha, this would be beta. If your beta carbon is a carboxylic acid, it will think of it just leaving because so it does this exchange of electrons where CO2 is able to leave and it tautomizes to a ketone or tautomizes back to a ketone. So malonic ester synthesis. So it's the same as it's kind of like the Claisen condensation where we have this ester and it does the SN2 attack and for here because this this carbonyl here, one of the carbonyls, their beta is a carboxylic acid. So once we treat it with a water and acid, it will turn the esters into carboxylic acids, kind of like this. So by doing so, um, we now have a beta carboxylic acid, and when that happens, decarboxylation occurs, especially if they in reaction they tell you to add heat, and so you lose one of the carboxylic acids and you just keep one of the carboxylic acids. So that's just a basic explanation, or basic way you could get it is when you have a nearby carboxylic acid that's 2 carbons away, you can just, it leaves when you add heat. Another one reaction is the HVZ, or Helvol-Hard-Zielinski reaction. So it's when you react PBr3. So here, the PBr3, it actually makes this into a good leaving group. So it will turn this into a OPBr3, and that makes a good leaving group for bromine to do an SN2 attack and form this. The reason why it also attaches here is because it can also this one can also get deprotonated from, yeah, this gets deprotonated, and so it can grab a bromine as well. So you get 2, and then when you add water, it's kind of like reacting a acyl chloride to make carboxylic acid, but here we have a bromine, so you just add water. Now water is basically a nucleophile that will replace this Br and get OH. Alright, so alpha beta unsaturated ketone and aldehyde additions. I don't know if your professor calls it this, but it's also known as Michael reaction. So here with aryl condensation, so if you just it's when an enol reacts with another carbonyl. So with that, if you have a if you have a molecule that looks like this, or it's a, yeah, so this is the product of a aryl condensation. So after you do an aryl condensation, you're left with this product where you have a carbonyl next to with an alpha beta alkene. So when you have that, you can actually react it with certain nucleophiles. So if you have hard nucleophiles are, these are examples, and soft nucleophiles are these. To figure out which one's hard or soft, soft nucleophiles are, you look at the lone pairs of the nucleophile. If they are stabilized by resonance or by electronegativity, they are soft nucleophiles. Like here, you can all resonate these, and these negative charges are also on electronegative atoms, kind of like Br or sulfur or oxygen. Whereas hard nucleophiles, you can't resonate the you can't resonate it to make a more stable compound. So another way you can tell is if you have metals as well. Here, this is an exception. The reason why this is a soft nucleophile is because these two charges cancel each other out in a way. And so here, if you number it 1, 2, 3, 4, 1, 2, 3, and 4, if it's a hard nucleophile, it'll do 1, 2 addition, where it will attack the number 2 position. If it's a soft nucleophile, it'll do a 1, 4 addition, where it will attack the alkene, the other alkene, the number 4 carbon instead. Right. And the last thing we're going to go over is the Robinson annulation. So it uses so it's when you have a alpha beta unsaturated ketone, which is a product of an alkyl condensation, and you react it with a cyclic ketone. Essentially, you're just this reaction is a way to add rings. So it'll do a 1,4 addition because enolates are soft nucleophiles, and so think of it as the ketone will. You can remove this oxygen in the ketone and just connect it, kind of like a puzzle, where we lose this double bond because this double bond is think of it as a connection to this carbon over here. But here are the steps. Let me see if I have the mechanism. Okay. So number 1, form enolate ion. So we form an enolate. And then next one is you do the 1,4 addition with the alpha beta unsaturated ketone. And you get this. You treat it. To get rid of this negative charge, you just react with water, and this is also called proper workup, where you just add a hydrogen there. It tautomerizes, which is third step. Tautomerize the enol, and you get a ketone. And it'll do it over again, except this the base will turn the other ketone into a enol instead of the original one. And so it does it again, where we do the aryl condensation, and we get a bond over here. Now it does an SN2 attack again. Let's see. Yeah, so the last step is aryl condensation. It does an SN2 attack once again, and then elimination to form that double bond back. And yeah, here's another easy way to do it. Yeah, so what you can do, you can just kind of line it up like this, and you form that ring where the double bonded oxygen was. That's where the double bond becomes, and you just remove the other double bond on the alpha beta ketone, and that should be it. Is there any other questions before we go to breakout rooms? All right, I can start. So let's look at this one. Let me turn my iPad real quick. Okay. So for this first question, oops, happened. Okay. You guys can see it. We'll try to go through it, but we're gonna post these review problems in the key as well. All right. So for the first one, rank the following carbonyl compounds by their equilibrium position in the following reaction. So, okay. So if we replace these R groups with the ones in the answer choices, is it going to go to the left or to the right? Right, so in order for us to get to this position, is we need to add alcohols to it, right? So when we add alcohols to a carbonyl, it's kind of like a nucleophilic attack. So we want this carbon here to be electrophilic, right? So when we add alkyl groups, so here these change because of we have alkyl groups. Alkyl groups are electron donating. Let me see if I can. Okay. Alkyl groups, electron donating, right? So we have, so looking at this one, the fourth one doesn't have any alkyl groups, so I would say that would be 5. Um, the last one would be 4 because we only have a methyl as an alkyl group. 3 would be, let's say this would be 3, because we still have this H there. Yeah, aldehydes react faster with than ketones. So then our next one would be the second one, and the first one would be the one on the left. So meaning this one would be further left, so less of this would form. Okay, so I'll take the next one.
Yeah. And just before I get started, I just wanted to ask everyone who's in the room, are there any questions that y'all want to focus on? We'll continue picking and choosing some questions to go over, but if you want to focus on ranking or reaction mechanisms, we can look at either. Just put it in the chat. But let's take a look at the second one. Oh, okay, reaction mechanisms. And actually, here, I'll do the second one, and then after we've done some of these ranking questions, we can definitely look at those. Let me see if I remember how to draw on here. Yeah. Okay, hopefully this will work. Right. So we're ranking the acidity of these molecules, right? So we've got an amine, alcohol, and then some carboxylic acid derivatives and a ketone, right? So what we're going to look at when we look at acidity is a lot of the same stuff that we looked at before. Can someone put in the chat what we're typically looking for in acidity? If not, we can also just do it on the side, which is fine. Charge separation is one of them, right? So we're going to look at charge separation in very big letters. And then we can also consider, let's see, we can consider resonance, right? So we can look at resonance, and also, let's say, the atom that carries that our charge after we've deprotonated our molecule, right? So taking a look at these molecules, we've got, let's see, where could we deprotonate these? So with our amine, we choose to deprotonate it at our amine, like our nitrogen, cross off that hydrogen. Same thing with our alcohol. We're going to do it at our most electronegative component. I'm going to put one in between our two carbonyls, because that would be our most stable position for a negative charge typically, right? You want to put it between two electron withdrawing groups, and then perhaps right here, or not here, right here. And then we'd put our negative charge, say, next to our carbonyl. And also, if anyone has questions, just feel free to put those in the chat. And then after that, what we're going to consider is we're going to look at, the way I like to look at it is we look at resonance first, and then we can look at our atoms and our charge separation as well, if we can find that, right? So here, let's look at this. Can anyone tell me which of these molecules, if we were to label them like 1, 2, 3, 4, 5, which ones have resonance? I'll give that like a second, but otherwise it's okay. Okay. Well, we'll say that we know that, yeah, so 3 and 4, these have resonance, right? Because we can resonate with our oxygens, such that, and we've got some adjacent double bonds going that we can resonate with, right? So we've got 3 and 4, and also our ketone, right? Because we can have our double bond come down, form our charge up down here, and put a negative charge up here, right? So we've got resonance in those last 3 structures, and then these 2 do not. They just have, like, they've been deprotonated, no resonance structures, right? And so based on that, we want to first rank all of the ones that have resonance. I like to put it as in, like, there's a first class form of acid and a second class, like a business, like there's business class and there's like economy. So like your resonance acids are flying in business, they get all of the priority, and then we look at everything else flying in economy. So here, when we're looking at these 3 molecules, we're going to be looking for some of the stuff Frank was talking about earlier. We're going to look at the number of resonance structures, and we're also going to look at electron withdrawing groups, how many are next to that negative charge. So for this one over here, we know that there are 2 electron withdrawing groups. And there is also this negative charge up here can resonate to either double bond. There's 2 double bonds that it can resonate with. So we're going to say that this one has some good resonance and electron withdrawing groups. Let's look at the other ones. This one over here, this 4th one, we have some good resonance as well. It has a couple of resonance structures it can form with, first, like this oxygen, and so a decent amount of resonance. And also, if it doesn't have a lot, it has 1 electron withdrawing group if you count that ester. And then in comparison to, let's say, like this ketone over here, this ketone has 1 resonance group, but then when we put the place that we've put that negative charge, it's next to 1 electron withdrawing group and then 1 electron donating group in the form of that methyl, right? So not as ideal. It's got an E electron donating group and an electron withdrawing group. So based on that, the way that we can rank this is that we can say, first, we have our anhydride sort of structure, or this is not an anhydride, but this 3rd structure as our most acidic, given that the negative charge is in a pretty stable position. There's a lot of different resonance forms and 2 electron withdrawing groups. We're going to choose our ester next, and then our ketone, right? And then after that, we can consider these 2 structures. First, between these 2, what we're going to consider is just the main difference you'll notice is that we have our negative charge on an oxygen for one of these and a negative charge on a nitrogen for the other. So the way we can rank that is looking at which one is more electronegative, which one is more able to hold that charge. You can also always reference the bean chart that we have, where you can put bean on the top left, B, and then AN, such that your acidity trends go to the right and down. So in that case, you'll notice that oxygen is more acidic. So we'll choose that as our 4 and amine as our 5. So does that make sense altogether? Any questions? If not, yeah, we can move on. Justin, do you want to take the next one, or are you just watching?
Yeah, I'll take the next one. All right, so with this one, this is another alpha carbon ranking question. So the first thing I would do is just figure out which alpha carbon we're going to be looking at in each molecule. So for some of them, we only have one option here. But for others, we have to pick between a couple of alpha carbons. So the rule is you want to pick where the negative charge you're going to put is going to have the most resonance. So in this one, it's going to be right in the middle, because now it can resonate with the 2 carbonyls. In our third example, we're going to put it in the middle here. I'm going to do it here. And finally, we're going to put it right here. So like we said before, the biggest factor is going to be resonance. So the first thing I'm going to do is figure out how many resonance forms each of these molecules have. So for this one, this has 1 resonance, 2 resonance, because the negative charge here can go towards that double bond with this one. This one will have 3 resonance, 2 resonance, and 1 resonance. So because resonance is the biggest factor, we're gonna say that our third example is going to be ranked the most acidic, because it's going to stabilize that anion the best. So now when we go to our 2 structures with 2 resonance forms, numbers 2 and 4, we notice that they both have 2 resonance forms. So the only other difference is this fluorine right here. So because we're dealing with anions, fluorine is a highly electronegative atom. So it's going to sort of spread that negative charge density away from the concentrated carbon. So it's going to help stabilize it more. And so fluorine is going to use its inductive effects to make this more acidic than this here. In the same way, now that we're on to 1 resonance, we're going to rank using fluorine once again, because it's going to stabilize the negative charge, making this 4 and this 5. Throughout all of this, we made sure that resonance was our most important factor, and then we noticed some key differences using inductive effects. Does anyone have any questions about this one before we move on? Okay, I think we're ready to. Oh.
All right. So for this one, I mean it's.
Oh, hold on.
Oh,
Someone
yeah,
had a question.
okay.
So, if you had a halide further down in the molecule, is it different? I would say that it won't be like to the same degree as if it's like right next to it, but it could still have an effect. But obviously, if it's closer, it's gonna be a stronger effect. Mm-hmm.
All right. So I want to skip this one and go to this reaction one. This is just like it's in the PowerPoint slide. It's just a review on the how you can get all the derivatives, how they connect with each other. But more specifically, oops, I think. Where do you guys want to start? I think we can do this. We can do this one. Or the third one. Oh, by the way, if you guys are changing the page, it also changes it for everyone. Okay.
I can take this Or do you want to take it, Frank?
You can take it.
No. You can take it. Sorry, I got confused. Don't worry.
Oh, okay. Okay, let's see. Let's all right, so let's look at this one right here. So here we're going from A. Let's look at A, right? So looking at A, well, let's look at the products and reactants, right? So our reactants and products. Um, the only difference I see is this turned into an is carbonyl turned into an alcohol, and we added uh, a methyl group. So do you guys know what we could do to add a methyl group? Yeah, yeah, you can actually do that. That's one way to do it. Let's see. Um, but another common way to do it is, no, actually, yeah, you're right. So we could do that. I think that's easier. Lithium with methyl attached, so I kind of like this. So this is a hard nucleophile, so it's gonna attack the. You'll do a 1,2 addition, right? And so that's how we get this um, thing over here. We get this methyl group on this side and not on the other alkene. So going to B, it looks like we're doing PCC. PCC is it's an oxidizer. So since we have a alcohol here, we can use PCC to oxidize it. However, it's a secondary alcohol, and the only way it could go is for it to become a ketone, right? Okay, so the next one, here we reacted with tosyl chloride. So with tosyl chloride, it just replaces the OH into OTS. So this is a good leaving group, right? So here we have PPH3, and AOH. So do you guys know what kind of reaction this is? Yeah, Wittig reaction, right? So since we're only given this, we're not giving like anything else. It looks like we're just preparing a yield. So, oops, what happened? Okay, so um, this one, I'll do like a SN2 attack, but essentially you'll end up with this right here. Like that. Right? Right, so with Wittig reactions, what happens when I react it a with this ketone? Any ideas? Yeah, yeah, yep. So I'll show the final reaction, but essentially this this PPH3 and the oxygen will bond together, and this two double bonds that they're connected to, they'll connect with each other. So this is what it'll look like. That let's and this. So this would be our reactant. So I mean, I could also make this the other way if I rotate this molecule for the other way, like this. However, this is less stable because our heavy groups are on the same side. So by making this, this makes it more stable because of there's less steric hindrance over here. Right, so that's and so now let's go to E. So this reaction is completed for us, this part over here. So it looks like we have this enolate. It reacts with this aldehyde, so that's how we. So here in this case, this is still a alpha beta carbon or alpha beta unsaturated aldehyde, and we have this enolate. So this would be a 1,4 or a 1,2 addition. So would it react on this carbon or would it react on this other carbon? Any ideas? Okay, so because this is an enolate, this is a soft nucleophile, so it's going to do 1,4. That's how it reacts over here. And then going from here to here, it looks like by the way, there's a typo here. This is just supposed to be a ester here from this side. Okay, so from here to here, it looks like I turned this aldehyde into a alcohol. So it looks like we reduced it. So if I reduce it, however, these two carbonyls weren't reduced, so the only reaction that we could do is probably the stab reagent. So stab is special because it doesn't reduce ketones in the presence of aldehydes. Right. And so the last step, we reacting it with an acid and water. So let's see. So for this one, since we're only given an acid and water, looks like it might react with itself. So let's look at our options. I would say, so these two lone pairs, right, they would get this hydrogen here, right? So this is what it will look like. Right, so we have a positive charge here. Okay. So because we added a hydrogen over here, so we can also add it to this alcohol here. The thing is that one of the two, they will attack. So if you put it here, it'll attack this side. If you put it on the alcohol, if the alcohol gets the proton, it will, this one would attack here. So it would still make a ring. So our final product after doing so, um, so let's go with the original one. So once we do an SN2 attack there, this alcohol will leave, and so this is what you get. Okay. Any other questions? Or do you have any questions regarding any of the reaction on this page? No, we can move on.
Okay. That was a really good set of reactions, Frank. I appreciated it. Let's see. Here. I'm gonna say we can skip over the nucleophiles for now. If anyone's interested, you can refer back to Frank's slides on the soft and strong nucleophiles. There's some good information on there about how to classify those for Michael additions. But let's see. What do we have on this next set? Okay. So let's take a look at this first one. It's been a second since I've used these drawing tools, but we've got it. Okay, so we're going to indicate the preferred product for the following reactions, right? So we're starting with this lovely reagent. Can anyone give a guess to what we might also call this? Something that may be a more familiar name for y'all? I'd say look at some of those beginning letters. That can always help. Okay. I believe that actually, oh no, I'm incorrect here. But it works like LAH. This is not exactly LAH. This is something called LTBA. Yeah. So we have, here, I'll put like a squiggle. It's sort of like LAH. So what LTBA does is it's a mild reducing agent, much like LAH, and it's really good at reducing a lot of carboxylic acid derivatives, with the exception of, I believe, esters. Let me check. Yeah. But in this case, we've got an acid chloride. And so what LTBA does is, instead of reducing it fully like LAH would reduce this to an alcohol, right? What LTBA does is it reduces only to an aldehyde. So you could almost consider this like one of those weak, like a weak oxidizing agent in the opposite direction, right? Remember how they could oxidize alcohols, primary alcohols, to aldehydes only? In this case, LTBA can only reduce acid chlorides down to an aldehyde, not an alcohol. So that's that reaction. Just remember to use it whenever you want to not go all the way to an alcohol. Right. Justin, do you want to take the next question? That, or I can finish this page and we can
I could do the next one.
Okay, let's do that.
Okay, so this one, our first step is adding magnesium. So magnesium reminds me of, whenever I see it, it reminds me of the Grignard reagent. So I noticed that we already have a bromine attached onto the molecule. So we're going to create the Grignard reagent like so. Sorry, I'm doing this on my mouse. It's not super precise. So now we have the Grignard. The second step is we're adding CO2. So if you remember the structure of CO2, it's carbon with 2 carbonyl groups. So the Grignard is able to act as a nucleophile to attack this carbon, move this up here, so that you eventually get let's see. And it will be O minus, and then the last step is the acid workup, which just turns this into OH. So this one's pretty straightforward. It's just creating a Grignard reagent to then attack the CO2.
Right. I can do the one next page. Oh, actually, no, let me see the bottom one. All right, so here we have a benzene ring with a ethyl group. Okay, and so first up we have this KMNO4. Whenever I see KMNO4, I see a bunch of oxygens, right? So here it's special in benzene rings, where it will completely eliminate this alkyl group and turn it into a carboxylic acid right there. All right, so next up is the saucil. So with saucil, I see chlorine on the reagent. So with saucil, what's special is that it'll make carboxylic acids into acid chlorides. So here, right? And so the last step is reacting it with another carboxylic acid. So um, think of it like, so here, um, this carboxylic acid, so we got some lone pairs here, can actually act as like a nucleophile. Attack this. Chlorine comes out. Chlorine is a good leaving group, and our final product should, so we still have the benzene ring. Should be this. Yeah. So as it attacks this carbonyl, um, this double bond will actually go up, and then it'll go back down. That's how it forms that's how it forms this ketone again. Yeah. So as it goes down, it'll kick off this chlorine. Okay. Have any questions? On to the next one.
Okay. Let's see.
Oh.
Oh, we can go back and look at that one.
Yeah. So
Oh, no,
which
sorry.
KMNO4? Oh, yeah. Sorry. For that one, um, because we have a benzene ring, um, you'll only need to know what kind. So I think you're asking if we should use acidic KMNO4 or basic KMNO4. So those only, yeah, those are that's what cleaves your rings. But with benzene rings, the double bonds on the benzene ring are really stable, so it wouldn't actually react the benzene ring. It'll just react with um, the alkyl groups on the benzene ring. But yeah, acidic is for alkenes and basic is for alkynes.
Okay. Right. We can move on to the next one. Let's see. What do we have here? Okay. I'm gonna see if I like any of these in specific. Otherwise, we can go down the row. Here.
I can do the one next
Uh-huh.
page. I think it's
Let's see.
and one more.
One more.
Wait, one more actually. I put a lot. Yeah,
That's
this one.
good. Okay, we can do this one. Okay, so we have to prepare. It's a synthesis problem. We love synthesis. So let's see. Right. So we've got a carbonyl with an alcohol also attached to an alkane chain, right? And then we're going to basically, the major difference that we see here is that we're adding these two methyl groups. So the question is, how can we do that? Let's find out. So one thing that we can consider is that what's one of the easiest ways for us to attach a carbon or like carbon chain to an like a molecule. Grignards, right? So yeah, Grignards, organometallic reagents, or you can use enolates. In this case, since we're attaching next to that alcohol, I'm sort of thinking maybe we can do Grignards. So we can actually, instead of working from this beginning step, we can sort of work backwards, where we can say, well, we could expect a Grignards reagent to fully saturate this with like methyls if we started with something that looked like this. Um, Perhaps just like we could do it with some sort of carboxylic acid derivative, including perhaps not a carboxylic acid, though we don't like to have acids, I believe, in Grignards. So we could instead do maybe an acid chloride. Let's see. Right, and that always makes for a really good leaving group. Right, because then we could expect that with some Grignard's reagent, possibly something that has just one methyl attached to the MTBR, we can have that Grignard's reaction occur twice, such that we'll see this carbonyl get attacked, and we can see our chloride leave. And that we can do that with excess, right? So that would mean that we could fully fill up all of those spots with methyls instead. But now the question is, how can we get to that step, right? Because in this case, there's still a lot of a difference between this initial step and like this acid chloride sort of step, right? So in that case, right, that is a good question. So, and that Frank brings up. So actually, that is something we want to consider. We want to make sure that this Grignards is focused. So something we'll want to do along the way is possibly protect the other ketone, right? So that we can see something like, maybe we can use an acetal, right? Some sort of protecting group, which tells us a couple things. One, we want to form some protecting group, right? And then two, we want to take our alcohol from an alcohol to an chloride, right? So now that we sort of have a game plan set out, let's see if we can fulfill those steps. Right, so let's just start with the protecting group, see what happens, right? That ketone doesn't seem to be doing much other than being there. So I think it would be nice to just protect it ahead of time, right? And if we use, say, a diol, we can target that ketone, right? So that would produce something that looks like this. And just a question, does anyone remember when, if we were choosing between a ketone and an aldehyde, which one would the diol first react with? Which one would the protecting group first protect? The aldehyde, right? Yeah, because the aldehyde is generally more reactive than our ketone. Perfect. So in this case, no such confusion. We can just continue, right? Yeah, it's also more electropositive. It has a more electrophilic carbon as well. So a little easier to attack. And in this case, now all we've got left is we have to form our acid chloride from our alcohol. So what are some steps we could take to do that? Here, I can give you a hint. One thing we can start with, yeah, SOCl2, right? But what do we have to do first? What can we use SOCl2 on? You have to oxidize it first, right? So we can use a strong oxidizing reagent, right? Let's say CHEM. Since we used that in our last problem, we do love to see it. It's also a lot easier to use in these theoretical reactions than in the lab. It's a heavy metal, so a little more dangerous in person than online. But in this case, yeah, so we're going to form our carboxylic acid, oxidizing it first. And then after that, we can absolutely use SOCl2 to form our acid chloride, right? And then from there on, we can use MTBR to add on those methyl groups. What else do we have to do after we use the MTBR? What else do we have to worry about? Can I go directly to this ketone form? Yeah, that's okay. So in this case, you can just use H+. You can use like an acid to just reform our ketone. So after we use our MTBR, we'd have another step where we use some acid maybe. to return our acetal back to our carbonyl group. Any questions about that set of steps? I know synthesis problems can be scary, but like a lot of it is deciding to work in both directions. So starting from here, you can tell that we need a Grignard's reagent. Frank pointed out an excellent thing. So when you're doing those reactions, also be checking for, are there anywhere else? Is there anywhere else something can react? Do I want to use a protecting group? And so that can help you start the other side of the reaction. And then as you work it through, you can sort of meet in that middle and figure out those intermediate steps as well. But any questions on that? Right. So if you want to protect just one of them, it gets a little complicated. So you have to choose the one that is more likely to be protected. So in between like an aldehyde and a ketone, you have to choose the aldehyde. In order to selectively protect something, let me think. It's not something I think about a lot. Justin and Frank, do you remember any specific ways that we could choose to protect like an aldehyde over a ketone? Or is that just not possible?
I'm trying to remember those. No, there's reagents that like specifically reduce aldehydes and stuff, but protecting it.
Yeah. But I'm not remembering which ones reducing agents.
You could reduce it, protect it, and then oxidize it back. I don't know.
Yeah.
You might have to. I don't know if there's like There might be selected like protecting groups, but yeah, I'm not quite sure.
It would be an interesting question. So definitely, if you figure out an answer for that, maybe you'll get a Nobel Prize. So who knows? Or there might be a Nobel Prize out for that already. So either way, win-win. And I know we have like 3 minutes left, but do we want to do another synthesis problem, or do we want to just sort of wrap some things up? If you have any specific questions, you can always talk about those. Oh, of the review or of the question section? Okay. Frank, if you want to tackle that question.
So I think you're referring to the part where I was going over the PowerPoint slides. Yeah, so we'll post the slides, the PowerPoint. We'll also post the videos for it. So we have a peer tutoring has a YouTube channel where we post all of our exam reviews. You should go over there. So we'll post it right after. So you can look through that. You can also look at the slides on your own as well. We'll also post a key as well to these practice problems if you want to work on other problems as well. Slides. Let's see. Where are we posting the slides?
The slides will be in the description of the YouTube video we post.
Okay.
So there'll be a drive link with the slides, the problem set, and the key.
Mhm. Yeah, it's no problem. We're always happy to help. Hope. So wish you good luck on your exam. Have a good night, and thank you for joining.
Yeah, and peer tutoring is open 6 days of the week, so you feel free to come by. We're always here.